Hi everyone, this is the fourth lecture of the control system series, and now let's see what we are going to study in this lecture. First, time response. Second, what are the types of input signals? Third, type and order of a system. And last, types of responses and some important terms related to those responses. Okay, so without any delay, let's start. Now, what is a time response? Okay, so it is how a system behaves with respect to time at a specific input. This is the definition of the time response which I have told you. अब इसको मतलब एक एग्जांपल से समझते हैं कि रिस्पॉन्स एक्चुअल में है क्या. ठीक है, जो जैसे समझते हैं कि हमारा जो ह्यूमन बिहेवियर है, ठीक है, वो भी एक तरीके का रिस्पॉन्स है. रिस्पॉन्स का मतलब नथिंग बट रिएक्शन. ठीक, किसी चीज के प्रति रिएक्शन. अब हम लोग जैसे ह्यूमन बिहेवियर है वो हर एक सिचुएशन में जो है अलग अलग तरीके से रिएक्ट करता है. जैसे कभी फियर होगा, जॉय होगा, लव होगा, इस तरीके के रिएक्शन हम लोग को मिलते हैं ह्यूमन बिहेवियर में. ठीक है, वो भी रहते हैं कि अलग अलग टाइम पे वो अलग अलग रिएक्शन हमारे सामने आते हैं. ठीक है, तो ये चीज होता है हमारा रिस्पॉन्स. अब रिस्पॉन्स ऑफ अ सिस्टम समझने के लिए ऐसे ही हमारा सिस्टम होता है, उसको भी मतलब जो सिस्टम के रिस्पॉन्स हैं उसको भी अलग अलग नाम दिए गए, जैसे कि अंडर डैम्प्ड, ओवर डैम्प्ड, क्रिटिकली डैम्प्ड, इस तरीके के नाम दिए गए हैं. उन लोग उस सबको हम मतलब आगे समझेंगे. we are going to study all that in this particular video. Okay, so now time response is divided into two parts. One is known as the transient response and another one is known as the steady state response. Okay, so a transient response is the response in which the system is subjected to a sudden change in input. Okay, ट्रांजिएंट रिस्पॉन्स में क्या होता है कि अगर कोई सिस्टम है उसके अक्रॉस सडन चेंज कर दे, तब उस सिस्टम का जो रिस्पॉन्स होगा थोड़े टाइम के लिए, तो उसको हम लोग ट्रांजिएंट बोलेंगे. एंड आफ्टर दैट ट्रांजिएंट पीरियड वी हैव द एक्चुअल रिस्पॉन्स ऑफ द सिस्टम. दैट रिस्पॉन्स, द एक्चुअल रिस्पॉन्स इज नोन एज द स्टेडी स्टेट रिस्पॉन्स. द time interval of this transient response is in order of nanoseconds or milliseconds, depending upon the type and nature of the system. Okay, so now let's take an example about transient response and steady state response. Here we have an RLC circuit, okay, which is supplied by a DC source V, and as we know that inductor opposes sudden change of current across it. Okay, and it acts as a short circuit in case of DC. 2 points are there for inductor, we know. So as we know that inductor will oppose the sudden change of current across this circuit. So at first we have current 0, then the current will increase gradually up to its maximum level. Okay, so we will have a curve like this. Up to this point, the response is known as transient response because this is opposing the sudden change of input due to inductor. So this response will be known as, this area will be known as the transient area, transient response, and after that the actual response of the system will be known as steady state response. This is a gap in between this line and the overall response. This is known as steady state error. We will understand steady state error after we will understand about the responses and all the things. Okay, for now we have a term known as steady state error. The gap between this is known as steady state error. Okay, so now moving on to next. Now, what are the types of input signals? I have already discussed these signals in the very first lecture of this series, so I'm moving a little fast here. to give a little knowledge to how to use these signals in this particular time response chapter. Okay, so I'm moving little fast here. First is unit impulse, which is given as this and represented by this. Second is, and third, fourth. These are the signals. Okay. Now, what about the Laplace transform? Let's have a short look at that also. One, for unit step 1 by s, unit ramp 1 upon s square, and parabolic it is 2 upon s cube or factorial 2 upon s cube. Both are same. Okay, so now moving on to the next topic. Type and order of a system. This is the most important and basic topic of this time response. Without understanding this thing, we cannot move further. Okay, so now let's understand what is type and order of a system. So first, type of a system. Number of single s in pole of a transfer function of a unity feedback system. Okay, single s pole. We will understand what does this mean, and also what the importance of a unity feedback system for determining the type of a system. This definition can also be explained in another manner, which is number of origin pole. Okay, number of origin pole, that how many poles we have at s equal to 0, that define the type of the system. So now understand the type of the system with some examples which we have. Suppose these 4 kinds of system we have given, and we have to determine the types of all these. Okay, so first, here we have no origin pole. Okay, so the type will be 0. Here we have one origin pole, only one, so the type will be 1. Here we have 2 origin pole, as you can see, s raised to the power 2, so type will be 2. Here we have 3 origin poles, so type will be 3. We will discuss about unity feedback system, why I am saying this. We will discuss about it, but before that, let's understand what is order. Order. Highest power of s in poles of a transfer function of a unity feedback system, or total number of poles, total number of roots, or total number of poles of a transfer function of a unity feedback system determines its order. Okay, so let's look over some examples that how can we determine order of a particular system. So here you can see that the highest power is 1, so order will be 1. The highest power is s square, so here type is 1, but order is s square. Okay, so order is 2. Here type is 2, but order is 2 and 1, 3. Maximum will be 3, so order is 3. Here type is 3, but order is 4. Now let's understand why I am saying this unity feedback system, this line, why I am saying this line. Let's understand this. Okay, so now let's understand it with help of an example. Suppose we have to find type and order of this given system. Suppose this is a system. Here we have s raised to the power 2 here, single s here, and rest are constant. We will discuss about these constants later, but let's only focus here for finding type and order, not over zeta, omega, n. We will discuss them later. Focus here for finding type and order only. So by looking at this, we can say that we have multiplication of s, like s equal to is 0. Single power or origin pole are 0, and highest power is 2. Highest power is 2. So type, we can say that type is equal to 0, and order is equal to, sorry about that, order is equal to 2. Okay, but my friends, this is wrong because we do not have this in the form of unity feedback. Type and order can't be determined until we have this system in the form of unity feedback. Okay, so let me erase this. This is wrong. Okay, so we can't determine type and order of a system until it is in form of unity feedback. It should be like this. Should be like this. Minus in here. Should be like this. Then the type and order can be found only. Otherwise, it will become wrong. So we have to do, we have to convert this system in form of the unity feedback system. And how we are going to do it? Let's see. Okay, let me erase this also. Yeah. So now, suppose we have converted this whole block into a form of unity feedback system. So this diagram should be equivalent to this diagram. So both the diagrams should be equivalent. So the overall transfer function of this will be, we apply the feedback rule here, gs upon 1 plus gs hs. So here hs is 1, so gs upon 1 plus gs will be equivalent to this thing, this whole transfer function. So it can be written as this, and this is the overall transfer function of this unity feedback function. Okay, so it can be written like this. Now let's solve this and find out the value of g. So moving on to the next, how we can find the value of g. Let's inverse on both sides, and by inversing we will get the LHS like this and RHS like this. Okay, and we separate two parts, like 1 upon g plus 1. Then take 1 this side. Okay, now by solving this, omega n square and here omega n square will get cancelled, and overall function will look like this. Now to find out the value of g, you can say it will look like omega n square upon s square plus 2 zeta omega n s. Now we will take s as common, and as a final result we will get this, which will look like this block diagram. Now we can determine the type and order of the system. So here origin pole is 1, means s equal to 0 is 1, and the overall poles are 2. So here the type will be 1 and order will be 2. Okay, so I hope you got this idea that how we are going to find type and order of a given system. First we have to convert it into a unity feedback system, then we have to find the type and order. Okay, so now moving on to next, types of responses. Now to understand types of responses, I have taken an example of a pendulum. So let's understand first type of response, which is underdamped response. We have a pendulum here, and now I will apply a little disturbance to this pendulum and see how in case of underdamped how this will oscillate. So disturbance will be in this direction. Okay, it is oscillating and now it will become stop. So here you can see that oscillations are of decaying type. Like in the first cycle it oscillates up to here, and in second little bit less, third more less, and finally it comes to a stable state with time. Okay, now this same things happen with our electrical system. which is an underdamped system. Okay, and the graph of that system is represented as this. This kind of response of an electrical system is known as underdamped response. Okay, I hope you got a little bit understanding of that. और let's understand this in हिंदी also. कि अब देखिए जैसे कि ये क्या होता है, हमने एक पेंडुलम लिया है, ठीक है, यहाँ पे ये हमारा पेंडुलम है। तो इसको जब हमने थोड़ा सा इस पे डिस्टरबेंस दिया इस डायरेक्शन में, ये आपके इस डायरेक्शन में जब हमने डिस्टरबेंस दिया, तो ये क्या है कि ऑसिलेट करने लगता है हमारा धीरे धीरे करके। पहले ज्यादा करेगा, फिर थोड़ा कम, फिर थोड़ा कम, ऐसे करते करते एक हमारा स्टेबल स्टेट पे आ जाएगा, ठीक है। तो यही सेम चीज होता है हमारा जो है इलेक्ट्रिकल सिस्टम के साथ। वो भी जब मतलब अगर उसका नेचर जो है अंडर डैम्प्ड है, तो वो इस तरीके से थोड़ी देर के लिए ऑसिलेट करेगा, फिर उसके बाद स्टेबल हो जाएगा। अब इसका क्या पैरामीटर्स है, कितना ऊपर जाएगा ये चीज, कितना नीचे आएगा, मतलब ये सारी चीजें स्टडी करेंगे। बट अभी हमें सिर्फ समझना है कि अंडर डैम्प्ड रिस्पॉन्स एक्चुअल में है क्या, तो इसमें हुआ क्या, ये ऊपर गया नीचे गया तुरंत, फिर थोड़ी देर के लिए ऑसिलेट हुआ, फिर स्टेबल हो गया। और इस तरह की जो ऑसिलेशन है इसको हम लोग कहेंगे डिकेइंग टाइप ऑसिलेशन, क्योंकि ये थोड़ा टाइम के साथ में ये खत्म हो रहा है, ठीक है। आई होप आप लोग इसको समझे होंगे। और नाउ मूविंग ऑन टू नेक्स्ट टाइप, overdamped response. Now let's take pendulum once again. Now let's see what happened when it is in overdamped condition. Okay, now let's see. Again disturbance will be in this direction. Okay, the pendulum comes to stable state very fast, like no oscillation are in overdamped, no, like no oscillation there, it comes to stable state really fast, ठीक है। Now let's see what will be the response of overdamped type of system. In case of electrical, it will also be the same. So for overdamped, the response will be this. But here the time for output to be settled, to get settled across this value will be more. Time will be more. So what we have to do if we want to settle it, but in less time, like if we want to settle it here, that kind of system is known as critically damped system or critically damped response. That type of response of the system will be known as critically damped response. So now let's see what is critically damped response. Let's take our pendulum here and disturbance will be in this side only. Okay. Now let's see what happened in critically damped. Okay. It is settled in no time. Absolutely no time. Okay. That is critical damped. Or the settling time is very less here. What is settling time we will understand. So also in the same in the electrical system it is also the same. It will settle but in very less time, less than the overdamped. Okay, that type of response is critically damped response. Now let's understand the next kind of response, undamped response. Now let's take our pendulum and let's apply a disturbance in this direction. Okay, let's see what happens in a undamped type of response. Sorry for that messy type of sketch, but I have to get an idea of oscillations only. So here you can see that oscillations are equal. They are not decaying with time. They are equal. So in undamped response, we can say that oscillations are never settled, or we can say in other words, they settled at infinity. The system is always oscillating in nature. So what will be the response of these kinds of system? It will look like this, always oscillating. The output is never settled, always oscillating. Okay. So these are the types of responses that a system undergoes, okay, or the system possesses. Now, moving on to next. Let's have a brief look over the responses in a table. Okay, what is stable and unstable response? In case of underdamped, overdamped, I'm going to tell you that over here only. So let me get the pointer. Now, as we can say that in case of stable system, the response is going to settle towards a point. Okay, it will go settle towards a point. But in case of unstable system, the response will tend to move to infinity. As you can see that here the response is not settling, it is moving. Okay, it will go to infinity like that. So this kind of system is unstable system, but the response is underdamped only. So underdamped unstable, underdamped stable. Now overdamped stable. This is overdamped stable and it is taking lot more time to settle. But what happens if overdamped unstable system is given? Overdamped unstable system will tend to infinity. As I told you that unstable systems are tends to infinity always. Okay, so it will look like this. Now for critically damped, it will same as underdamped response, but the settling time will be low. So it is given as this. The system is settled very soon or in no time, settled in no time. But what happens if critically damped system is unstable? The response will go to infinity like this, like this. Now, a third type of system is marginally stable system, or the response of this marginally stable system is undamped type. So the response will be given as this. As we studied about the undamped system, non-decaying type oscillation, and the system will oscillate up to infinity. Okay, so this is a brief idea about the responses we have learned. I hope you have understand the responses of electrical system. Now moving on to next, some important terms, parameters or specification regarding the time response, which we are going to derive in our next session for different types of system uh, that are responding to different types of input. Okay, so now the first parameter is rise time. Okay, so time taken by the response to reach from 0% to 100% in the first cycle, in the very first cycle, is called as rise time. For overdamped, it is 10 to 90%. For critically damped, it is 5 to 95%. Now let's have a graphical representation how a rise time is pointed in a graph. Okay, so this, as I've told you, for the first time, 0 to 100%, this is our 100%, not this. This line is our 100% response. 0 to 100% for the first time is known as rise time. This thing, this time from here to here, this is our rise time. Okay. Next term is delay time. What is delay time? The time at which the response reach from 0 to 50% of its value. ठीक है, मतलब 0 से 50% हो जाएगा, उतने में जितना टाइम लगेगा उसको जो है डिले टाइम कहते हैं. ग्राफ में देखते हैं कैसा दिखता है. लेट्स टेक अ लुक ओवर द ग्राफ. Okay, this is 0.5 here, and this time is delay time. Now next term is peak time. अब आउटपुट जो है पहली बार अपनी पीक पे पहुंचता है. ठीक है, पहली बार अपने पीक पे पहुंचता है, उसके लिए जितना टाइम लगता है उसको पीक टाइम कहते हैं. ठीक है, व्हेन द आउटपुट रीचेस इट्स पीक एट फर्स्ट टाइम, so that time is known as the peak time. Okay, let's see how it look like. As you can see, peak is here and the time taken is this much. So this from here to here is the peak time. Okay. Now let's move to next, settling time. Time taken by the response to reach its steady state. Steady state means as you have seen that dotted line CT, that is a steady state. We will discuss what is steady state later. Okay, the time taken by the response to reach its steady state value at 2 or 5% tolerance. We will also understand this, what is 2 or 5% tolerance and what is steady state later. Let's see what is settling time. This time, the time taken by the output, simply it is the time taken by the output to get settled to its final value. Okay, this thing is steady state. And as I've told you, there is a difference between these two lines. This is known as the steady state error. We will understand what is steady state and steady state error later. But first now understand what is settling time. So time for the response to get settled to its final value is known as settling time. It is given for 2% and 5% tolerance. We will also going to understand what is that. Now first here for the definition only we have to study here the settling time only. So this time from here to here is known as the settling time. Now next term is maximum or peak overshoot. It is a difference between time response peak and steady state value. Let's understand this by graph. This is known as the maximum peak overshoot, this value, and it is a difference of steady state value. As I've told you, this is the steady state value represented by C infinite, and peak value. Okay, this is the peak value. So the difference of these two values known as the maximum or peak overshoot. It is given mathematically given by this, and in a form of percentage. In a form of percentage, it is given by this. Okay. So now let's move on to the next term. Time constant. It is a time at which the response of the system reach to 63%, approximately 63% of its steady state value. Okay. So another definition of time constant is given like a time which represents the speed with which a particular system can respond to change, or it is equal to the time taken for a specified parameter of the system to vary by a factor of 0.6321 or 63.21%, or nearly 63% we can say. So for time constant for in this control system or any system is given by -1 upon real part of smallest pole, or you can say mod of 1 upon real part of smallest pole. Real part, we will not take imaginary part in here. Okay, so let's wind up here, and we will meet in the next class where we are going to discuss the response of certain system, and we will calculate these parameters like rise time, peak time, delay time, time constant, peak overshoot, etc. Okay, so thank you.